Hello, this is John Everest, and this is the second of a series of brief tutorials on, not so much tutorials, discussions on the phase methods for calculating daylight. In the previous tutorial, I just wanted to emphasize to you the concept of how a continuous sky dome becomes divided into a number of patches, and the relationship between each patch and our area of interest. That a coefficient is produced for the efficiency of light transfer from each patch to each point of interest for our calculation. The reason we do that is to avoid having to constantly recalculate or ray trace every single sky step. So we just stepped on to actually with that background knowledge. Here's that divided sky dome. We just sort of move forward to talk about the actual methods. And I'm going to start off with the two phase. I'll just briefly sort of make you aware of the other phases, and then I'll touch on the two phase, and it is actually the most simplest. Two phase is also referred to as the coefficient method. Because it is the coefficient figures from the sky to the points of interest. So a two phase is simply sky dome here, and phase one, phase two, sky dome, calculation points, or if it's a rendering, it will be all the surfaces. A three phase is the sky dome to the window to the to again the calculation points. 1, 2, 3. Is it going to show a four phase? Four phase. A four phase is sky to your external sort of fenestrations to the window to the points inside. 1, 2, 3, 4. And actually five phase gets five and six phase are something else. I'll come to those later. It's a sort of it's like a four phase, then a sort of an additional more accurate 1, 2 calculation for the sun. So that's sort of like your 1, 2, 3, 4, 5, 6, and that I just want to give that a little bit more discussion. But with that being said, let's go back to a two phase, and I think I'll just be able to sum this up very quickly. When you are doing a two phase calculation, if for example you're using the classic DaySim software, or you are simply just doing a daylight coefficient method, you will be using the two phase method whether you're aware of it or not. And as I say, what you are doing is for every hour of the year you are just simply the computer is working out the accuracy between the efficiency of the transfer of every patch of the sky to every point in your room. So it's simply from there to there. That is an accurate calculation. Relative to some of the things I'll discuss on the other ones, there is an accuracy there. The potential inaccuracies are the fact that you are loading all of that sky's energy simply into you're sort of compressing all that sky's energy into that central point there. So should it, by coincidence, should it be that like a window mullion, or maybe I can draw that on. Imagine if you had a sort of a window mullion, and this is representative of the sun, and I'll touch on that in a moment. And imagine if there's where all that energy is loaded into that single point, and just imagine by coincidence that should that point, I can't be bothered changing the color, should the light come down, and should that point sort of intersect with the window mullion, all that energy does not enter the room, so there is an inaccuracy there. And the bigger these squares are, imagine if that square was even bigger, like that, then you've lost, you have an even bigger inaccuracy for that, which is why, and I'm sort of going to I'll come on to this later on. You can actually choose to reduce the size of your sky patches, and it's there. Yeah, so you can divide it into 145. Oh, I'm back on my version. I better stop scribbling. You can do 145, you can do 580, and you can do 2. you can go on, and then you can go on to 2300, and yeah, and it keeps going. But of course, you're I mean, that's like, like three times more ray trace pieces to calculate, and then that is, gosh, who knows, like, what would that be, like more than 10 times, like, yeah, more than that. So you get more accuracy, but your calculation period gets significantly longer. Another 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 issue with dividing the sky dome, and really I should have discussed this on the when I was talking about sky domes, but I'm looking for that picture of the two phase there. Is what it's doing when it does. Obviously, the sun is a point source. The sun in the sky is going to be so big. In these calculations, the sun is taken to be that big. So again, you have, I mean, there's a huge quantity of light that comes from the sun, so you have a huge inaccuracy there. And it is the 5 phase and the 6 phase, and actually what's called the coefficient DDS calculation that will help to correct that, which I will come on to later on. But that's how that bit works. So why, if it has reasonable accuracy, why would we do anything else? And the issue with this is, imagine if you do a calculation and let's say something has changed inside the room. Yeah, so let's say we've decided we are going to paint this wall a darker color. So now we need to recalculate our daylight performance. Nothing has changed outside. It's just inside that's changed. But because everything is calculated at the same time, we now have to recalculate everything. So even though nothing changed out here, we still have to recalculate all this area because we changed something inside. So there is a lack of flexibility. So the price you pay for the simplicity, there's less data to manage, and there's arguably a degree of superior accuracy of sorts in that when we go into the three-phase method, you'll see how simplifications are made. Should you change anything on this side, you have to recalculate everything. Or if nothing changes, imagine if nothing changes in your room. And in fact, a more probable scenario would be, imagine like you had a series of classrooms. Imagine you had a building and it was divided up into a series of like pod offices or classrooms like so. And the windows are here. This is a plan view, yeah. And you've got windows here. Inside every single room is identical, right? But imagine, let's just say for this classroom, there's, I don't know, let's say there's a tree actually. There's a tree in front of this window. We could on other methods, we could reuse the internal calculations and just recalculate the exterior because everything is exactly the same. If you are using the two-phase method, it's because all the calculations happen at exactly the same the calculation happens at the same time for the exterior and the interior. You will have to do completely fresh calculations for every single room, and usually in fact every calc I've ever done is the longest calculation is the internal bit. The external is really just identifying the coarse geometry and factoring that in. So that is the two-phase method. It's the simplest method. It has there's less risk that you could sort of get things going wrong. It keeps a good accuracy as it's so like it will pick up these fenestrations reasonably well. Relative to the size of the sky patches you are using. The downside is that there is a lack of flexibility. There is an unbreakable linkage between the interior and the exterior. If one changes, you will have to recalculate the other. Okay, and the three-phase, and I'll come on to next, will address that.